Hello, everybody, and welcome to this month's Future in Space Hangout. My name is Tony Darnell. I'm with DeepAstronomy, and we do these every single month, so I'm really excited with this is the week we get to do our Future in Space Hangout. These hangouts, by the way, in case you don't know what they're all about, are designed to kind of bring in both engineers and scientists from both the American Astronomical Society and the American Astronautical Society, double ASs, both of them, to sort of talk about our future in space, both in manned, in human space flight, as well as robotic space, and also the science associated with them. So that includes just about everything up in space, like the James Webb Space Telescope and all kinds of other things. So that's what we're doing. These hangouts can be are held the third Friday of every month. So we hope you will subscribe to my Deep Astronomy YouTube channel, or that's one way to get notified. And another way is to subscribe to the Facebook page for Deep Astronomy. It's facebook.com/deepastronomy/events. And just hit the subscribe button, and I post them all there. And once it's posted, you'll be bothered incessantly by Facebook. I'm kidding, not really. But they will remind you when an event is going or happening if you say yes to it. It's also on G+ as well. So that's what we're doing each month, and we're kind of getting our feet under us now with these. This is like our sixth one.
About our sixth, yeah, about our sixth or seventh.
Yeah, so we're kind of getting our feet under. We've got a lot of great ones so far. We've talked about gravitational waves. We've talked about LIGO. We've talked about exoplanets. So and WFIRST, all kinds of stuff. So we hope you'll keep going. And as part of the spirit of these hangouts, well, before I get started with that, let me go ahead and introduce my co-hosts. With me is my two co-hosts, Dr. Harley Thronson. He's an astrophysicist at the NASA Goddard Space Flight Center, and this is his sort of brainchild. He helps keep these going each month. Hi, Harley. Welcome back.
Hey, good afternoon, Tony. Glad to be back.
I'm glad you're back, too. You just got back from a long trip, didn't you?
I did. Spain is lovely. Strongly recommended.
I'm planning on going myself soon, I hope. And also joining me as he does each month is Dr. Alberto Conti. He is an innovation scientist at the Northrop Grumman Corporation. Hi, Alberto. Welcome back.
Thank you. I'm joining you from. You can see a busy crowd behind me. I'm at South by Southwest at the JWST booth. So hi everybody. Hi Harley.
So what's going on? Give us an update of what's going on out there. What's it like for now? This is like the third or fourth year JWST has done something out in South by Southwest.
Yes, right? That's right. So maybe I can even walk around actually and show you what's behind me. Actually, we have a very, very large booth here at South by Southwest. We're doing a lot of interesting things. We're showcasing basically the progress of the telescope with NASA and with the Space Telescope Science Institute, where I used to work for many years, as you know.
Right.
It's a busy time today. It's we opened a few minutes ago. We're going on pretty strong, so we have an interesting mural there from the Hubble Space Telescope, and a 100 million stars. So it's a hectic time.
It's the FAT survey.
Correct, the FAT survey. So we always tell people to actually go and take a look and how 100 million stars look. So it's fun, and I have a fast wireless, as you can tell, which is unbelievable.
Yeah, I can't believe it. So, for those of you who might be in the Austin area, are you at the interactive exhibit?
Yes, we're at the Gimme convention. So come here. If you ask me a question,
it's free.
It's free. If you ask me a question, you get a nice JWST pin. So come on, ask me a hard question about JWST, and you get a pin.
That's great. Good. Well, yeah. So I love going there. I've gone there twice, and it's really crazy out there. But the interactive is the interactive exhibit is one of the few free things that's going on out there. So you can so head on out there if you're in Austin and say hello to Alberto. How long are you out there for, Alberto?
I'm actually leaving tomorrow, but the gaming is open until tomorrow. So all day today, all day tomorrow. It started yesterday.
Okay, don't move around too much. You're starting to mess up your bandwidth now. So it's very adventurous of you to. Okay. All right.
Back.
So, good. Excellent. Okay. So like I was starting to say before I introduced my co-host, was that we want you to interact with us. And right now, there are 3 now ways you can do it. I've added a new one here today that we can do, but I've got the easiest way is if you're watching this on YouTube, the live chat is currently enabled, and so please get on there and leave us questions and comments, and I will read directly from the chat window itself. I also am looking at the Future in Space hashtag. It's right down there on my lower third there. So if you tweet at us on using the Future in Space Hangout, I will read that as well. And finally, I have an email address for this now. It's really fancy. Email us at futureinspace@deepastronomy.com, and I can also read your questions from there. Okay, so let's go ahead and get started. I'd like to introduce my guests. They are. We have Dr. Keith. Oh my gosh, I forgot to ask how to pronounce your last name. Could you pronounce your last name for me, Keith?
This is Keith Gendreau.
Gendreau. Okay, good. He's an astrophysicist at Goddard Space Flight Center. He works in the X-ray astrophysics branch, and he is a member of the NICER committee. That's such a pleasant name for a mission, NICER. I like that. the NICER project on the ISS, and also joining me is John York. John, he's an atmospheric scientist at Goddard, working at the mesoscale atmospheric. I can't read my writing. What was the other branch?
Yeah, mesoscale atmospheric processes branch.
Processes branch. I wrote it so badly. It just looks great. Well, so welcome, guys. It's good to have you on board. Now, you guys both operate missions on the International Space Station, and I don't know if mission's the right word. Am I calling it the right thing? What should I call that? Is missions okay?
Yeah, in the case of NICER, we consider it a mission of opportunity. It's a small, complete mission.
Okay, but these are essentially projects that run in some capacity either in or on the International Space Station, right?
Yes.
Okay, cool. So, we want to talk about this. I want to talk about those missions and everything else before we get going. But I just want to point out that the International Space Station has been around for quite a while, as we all know, and most recently, the record holder, the American record holder for the longest spaceflight duration, the astronaut just came back from that, and they're currently studying the effects of long duration spaceflight. That's certainly been one of the main uses of the International Space Station. But over the years, it's kind of been through a lot of incarnations, hasn't it, Harley? I mean, I can remember back in I think it was the 90s, that the International Space Station wasn't really called that. It was called other things beforehand, and it kind of morphed and got redesigned over the years into what it's been become now. It's been kind of a political thing, and in addition to that, it's been sort of a science. If I had any complaint about the International Space Station, it was it didn't seem to have a lot of focus early on. But can you give us a little background on some of the things that the ISS has been sort of...
Sure. Now, the various names that your audience and you may know were different names, like Alpha, Space Station Freedom, and so on. Those were different names of earlier design work. The name International Space Station has stuck since construction began in the, let's see, good heavens, I'm going to embarrass myself. I think 1990 was when it was first occupied by humans, and it's been occupied constantly since then. It was for many years quite appropriately known as an enormously successful, perhaps the most successful, truly major engineering project, civilian engineering project, civilian international engineering project of all time. And however, over about and again, I'm sort of probably dating myself, probably the last half decade, maybe 7 or 8 years, with it fully fully completed construction, applications for the space station now have become more widely known and more widely available. The space station is a key stepping stone in human spaceflight for eventual long-duration travel beyond the immediate vicinity of the Earth. That's for a different topic, another one of our hangouts. But for the purpose of this particular hangout, a number of us, Keith and John and a large handful of others, recognized, once again, sort of like a half decade ago, that the space station offered a terrific, for the right kind of science program, a terrific platform for carrying out relatively modest cost and important scientific experiments. So there has been a growing interest. John and Keith are going to be describing 2 examples. There's been growing interest in the capabilities of the space station for these very capable and relatively modest cost missions. projects, instruments.
Yes, so it's been a long road, and a lot of use, a lot of good stuff has come out of the space station. Of course, I used to love watching the space shuttle get close to it, and they do these really, but whenever they went to the space shuttle, they did this inspection flip that always was so impressive whenever they did that up there. And of course, we've seen all the images and the photos that the astronauts take up there. It's been really great.
And one thing I wanted to add, actually, he has grown over the years. So, since 1998, when the first module launched, is now the largest artificial body, if we can call it that, into orbit. And actually, you can actually see it pretty easily. So if you can track it, you can actually see it.
Oh yeah, and NASA has a website. Where's the ISS?
Yep.
You can go to.
Right.
And being in the UK, it actually flies over the UK quite a bit right now, and it's amazing. I've gone outside and seen it. Just it's really, really bright, and even with the pair of binoculars, you can kind of see maybe some detail to it, but not very much. Telescopes and fast tracking things would get you a lot better. Maybe you can image it, and people are imaging it all the time, but it is an amazing thing to watch, and it really scoots across the sky too. So yes, you can see it very well, very easily with your naked eye if you happen to be underneath it when it's going by. And the way to find out is just go to nasa.gov. I think it's called Where is ISS, and it'll tell you when and where it's visible on any given date and time. So that's kind of cool. Okay, so let's get to some of the missions that we came here to talk about. I'm going to start with. I think with Keith. Keith, you run what's called the NICER mission. Is that right? Why don't you tell us what that's about?
Okay, so NICER stands for the Neutron Star Interior Composition Explorer. That's a mouthful. It used to just be NICE in a previous iteration.
But it got better, obviously.
It got better, yeah. So it did. So NICER is actually the first competitively selected astrophysics mission to go to the International Space Station. Meaning what we did was we spent about 3 to 6 months putting together a proposal and an instrument and a mission and a science concept that was put into the NASA Science Mission Directorate Explorer call in 2011. We competed against about roughly 40 or 50 other concepts, and then we did very well. And a second set of a little bit more detailed follow-up study. We were down-selected, or up-selected, I should say, to actually continue on with the mission. And so we are actually at a point right now on NICER where I just walked from Building 7 over here at Goddard, where we do a lot of our mission integration and testing, and we just pulled the NICER payload out of a large thermal vacuum chamber where we simulate its time and space, make sure that it can function under the extreme thermal environments that we expect. And it did, and that's one of many environmental tests that we do. We are on track to package it up in the next couple months and deliver it to Kennedy Space Center in June. We were supposed to go up this coming August for a SpaceX 11 resupply mission launch that would bring us up to the space station. But our launch date has moved to the right. Right now, we're looking at a January launch. But our instrument is ready. Our science team is ready, and it's quite fantastic. Did
that freak you out when they moved you from August to June?
Oh yeah, it freaked me out a lot. They in about a month period they moved us from August to June, and then a week later to March, and then they said back to January, and so yeah, I want to get up there as soon as we can.
I have your little graphic here that you showed me about the it's sort of the header of the whole thing, the sort of a mission flowchart kind of thing, where you're going to be launching this. It looks like on a Falcon 9 rocket in June, correct?
In January, I should say, January. We're delivering to Kennedy in June, but we're launching right now, most likely in January.
Oh, I see.
We're going on a Falcon 9 rocket, and if you look at that little picture to the left, the lower left, that's a Dragon capsule. The top of it has a pressurized chamber that brings up supplies to the space station, food and other types of things that require some sort of atmospheric pressure. But underneath it, there's something called the trunk. And the trunk is for unpressurized experiments that would be mounted to the outside of the space station. NICER is going to be put there with 2 other experiments. And then we launch on the Falcon 9 rocket.
Right here.
We are then berthed with the International Space Station. And then after a few days, the ISS robotic infrastructure extracts us from the trunk, and then we're robotically placed at what's one of the remote ports called the Express Logistics Carrier, or ELC2 ports. And in that graphic, it's one of the tall vertical fins to the left of the International Space Station. It's all done robotically. We don't actually use the astronauts for any of this, except possibly some of the berthing of the vehicle. But the operations with NICER itself are all done robotically.
And well, who's operating the robots though? Not astronauts?
No, it's somebody in Canada. Canada runs it's the International Space Station.
What is it with Canada and those robot arms? Do they have the monopoly on robot arms? Are they the ones that have them all? Nobody else?
It seems like that. I don't know the whole deal there, but you see Canada written on all those arms, and including back when it was in the space shuttle.
I know. I remember that. Yeah.
So
Canada's going to do all this operating from the ground. It looks like, to get it up and going where it's going to be. And this flow chart kind of shows the progression.
Right.
And where it's going to sit is right here. Right next to these giant solar arrays. So that's
that's right. We actually swing within a couple feet of the solar arrays that power the entire space station. And so we worked very closely with the space station engineers, including the safety office, to make sure that we would be of no danger to the space station or the astronauts. That's actually one of our design drivers for actually any experiment that goes to the space station. You can't do any harm. And if you can assure that you don't do any harm, I think it's a fantastic opportunity to do science at a relatively low cost to the science community of NASA.
Okay, well, let's talk about your science. So once it gets up there, what are you going to be doing with it? What are you guys hoping? What's your science goal? What's your main science goal?
Okay, so from the name, Neutron Star Interior Composition Explorer, you can imagine we're going to look at neutron stars. A neutron star is really the densest matter in the universe. It's a star that started its life almost 10 times the mass of our sun. It consumes all of its nuclear fuel, fusing hydrogen into helium and so on, until it can't do fusion anymore. At that point, gravity takes over, and that star explodes in a supernova explosion. When the final result of that explosion is a small cinder that weighs about 1.5 times the mass of our sun, but can be 20 or 30 kilometers across. So if you can imagine all the mass in our solar system, dominated by the sun, squeezed into something the size of Washington, D.C., that's the kind of object that we have. It's the densest matter we know in the universe. If that original star was somewhat more massive, the result of that supernova explosion would have been a black hole.
So it's kind of, the next step, but if it's a little bit heavier, it would have been a black hole.
Right. So
so let me just to interrupt you real quick. The pulsar at the center of the Crab Nebula, isn't that a neutron star? It's just rapidly spinning?
Yeah, that is a neutron star. So that's actually one of the most famous neutron stars.
Right. That's why I was hoping to make that connection.
NICER.
Know about it.
So some neutron stars are called pulsars, and that's because they have hot spots that are on them, and these hot spots rotate as the neutron star rotates. Physics is applied at all points in the production and the lifetime of a neutron star, and so you can imagine this massive star was spinning slowly. At the end of the process that produced a neutron star, that was much, much smaller in radius, it spins up just like an ice skater. When she pulls her arms in, she spins more rapidly, and the same thing happens with a neutron star. And some of these neutron stars are spinning many, many times a second. The Crab pulsar is spinning about 33 times a second, but there are some that spin hundreds of times a second. And they pulse because these hot spots rotate in and out of your field of view, and from your perspective, they seem to blink. So neutron stars were discovered in the year I was born, in 1967, but in the radio band.
Oh, okay.
And it was very creepy because I saw regular pulses from the sky, and they didn't know what it was.
That's right. That was the same antenna, wasn't it? Or maybe it wasn't. There was an antenna that discovered the Penzias and Wilson. Their antenna found.
No, it's a different one.
Background.
This is a different antenna, but it was a very interesting object. They ended up designating that object LGM-1 for Little Green Men 1.
Right.
So regular.
Yeah.
And in fact, since that time, we've now discovered thousands of neutron stars. Many of them are pulsars, and some of these pulsars have pulse regularity. I mean, they tick with a regularity that's as stable as an atomic clock or better. And so, while our neutron star science is to understand the physics of the interior composition of a neutron star, measuring exactly the radius, we're also doing a very interesting technology demo where we use these pulsars as high-precision clocks, just like we use the atomic clocks of GPS. And the idea is that GPS satellites have atomic clocks that transmit their time. Your GPS receiver receives multiple times, and applying a little bit of math and physics, you can figure out where you are anywhere on the Earth or in low Earth orbit. GPS satellites do not work to give you a position around Pluto, but our pulsars are distributed around the galaxy. And so we want to do a technology demonstration where we use these pulsars to simulate, to basically be the natural infrastructure for a GPS-like navigation system that'll work throughout the solar system and into the galaxy. And in fact, I believe that in several hundred years, when we leave the solar system, it'll be navigating with these types of objects with the technology that we're going to demonstrate as part of this mission.
So we will change the first G not for ground but for galaxy.
That's right. Galaxy positioning system.
I love it. It's a great idea, and those, as you mentioned, many of those pulsars are extremely stable. So how many will you need actually to have a galaxy positioning system, though?
So
precise, I mean, it depends on how precise you want to be, obviously, and where you want to locate.
Yeah. So 3 or 4 allow you to get 3-dimensional positions.
Yep.
We believe there are about a dozen that have about the right characteristics that we need. And really, we want to use it in concert with other deep space navigation techniques. So you might even be able to use 1 or 2 in conjunction with deep space network ranging to give you a more complete picture of where you are in the solar system.
So just to give an idea to people that don't realize this, how precise are these pulses from neutron stars?
Well, like I said, on timescales of years, some of them are more stable than the ticks you hear from an atomic clock, which is the most stable, clocks that man have made. Not all of them are like that. The Crab pulsar, which is a very famous one, unfortunately has star quakes and kind of glitches a little bit, and so it's not the best for timing. But even with that, we can do some navigation demonstrations, and we can clearly do our science with those types of objects.
Well, at least you don't have to change the GPS acronym, do you? I mean, it's a galactic positioning system. It's all the same, so you don't have to change it, right?
Yeah, I like it. And they eventually, Keith, they do slow down, obviously, but on astronomical time scales, obviously.
Yes. So as they're slowly losing energy emitting this radiation that we're seeing, and in other terms, they will slowly slow down. But we can actually track that and put that into a navigation model.
Perfect. Fascinating.
Okay, so I've got this thing up here that you gave us. Let me make it big here. These are is this something called the pointings, right?
Yeah, actually, could you go to? There's another one called deploy and track, and I just want to show you how.
Okay, let me get to it. Deploy and track. There it is. Okay. Can you see it?
Yep.
All right, it's up. Should be up now.
Okay, so
I'll
we
start.
go up as a small little box in the back of the Dragon, but then to get a view of the sky, we have to unfurl. So what you see here is how we unfurl and then can swing around. So this is an X-ray telescope, that big box, and this is going much faster than real time, but the idea is that as the space station goes around the Earth, we can watch a neutron star or any kind of astronomical object rise off the horizon of the Earth, and then we can track it until it sets, and then pick up another target, and we do this continuously. So every 90-minute ISS orbit, we will typically track between 2 and 4 celestial objects and collect our data over time.
What exactly are you collecting? What wavelengths here? What are we looking? What are you looking at?
These are X-rays, so not high-energy X-rays. These are X-rays in the 200 eV to 10 kilovolt bandpass, which is where neutron stars are very bright. It's much softer than, say, medical X-rays, which are more in the 60 kilovolt range and higher. So we have X-ray optics at the front that capture photons from neutron stars or whatever we're looking at, and then we direct them down to detectors that can detect individual X-ray photons. We measure the arrival time of every photon very accurately. We measure the energy of every photon very accurately. In fact, NICER, compared to the last X-ray timing mission, has an order of magnitude better time resolution, energy resolution, and sensitivity. So we're expecting to do a lot of science with NICER.
And how long is this expected to run? This telescope?
We have no consumables. We have gimbals and actuators that allow us to swivel and point and get a view of the sky. They should last decades. Now, reality is we have to show that our science yield is very high, and so we are required to produce a lot of very good science papers that we then could turn into independent science review panels that would allow us to continue operational funding of the mission. Right now, we have at least 18 months on orbit to do neutron star science, but we plan to go on much longer.
Great. Okay. And then we have this other one here that you wanted to show. Was what was it called here?
NICER pointing. Yeah.
Pointings. Yeah. You want to let me pull that up here.
Yeah. So this one just kind of gives you. It's kind of a rehash of what I just told you there, but it gives you an idea of our proximity to things like solar panels and the types of problems that we run into. When I grew up, I had a small little telescope, and I'd go in my front yard to look at stars and galaxies and nebula, and I had to plan based on where the trees and the street lights were in my neighborhood and what I can see at what time of the year. On the space station, we're 2 feet away to these gigantic solar panels that are moving. These are kind of our trees there. And what you see in this animation is the result of a simulation that we did very early to make sure that we could do astrophysics from the space station with all these moving parts. And so, from a simulation that made that animation, we convinced ourselves that more than half the time we're on space station, we're going to be doing useful astrophysics science, which is pretty comparable to what Hubble does.
Okay.
Yeah.
Awesome. Well,
Can I ask you a question, actually, Keith? So, I mean, you described pretty well the requirement that you had when you went to the space station. But so, was there something that was worrying you more than anything else, when developing the mission, given that it's on the space station and it's not free floating?
Well, so like I said before, NICER was NICER. It was just nice, and that was the first proposal we put to the space station.
Before nice, it was not that nice or ugly or something. No.
No, actually. So the very first iteration we put together of this experiment as a proposal for going up to the space station, we were concerned because we were competing against other things that weren't going to the space station, and there was a general feeling in the community that, astronaut safety, all these things could make it so impossible to actually do anything useful on space station. And indeed, in the early days when we were writing the NICE proposal, it was not so much of a good user interface to scientists to do a mission like this. But since between NICE and NICER, we've seen a tremendous change in how the ISS works with science teams to put experiments on the station. And we got integrated with really a fantastic team, on the International Space Station project. People from Johnson Space Center, from Marshall Space Center, Kennedy, all over, who worked really closely with us to make NICER compatible with the space station and make it really a bargain to the Science Mission Directorate, which is paying for this. This is called a mission of opportunity because of that.
Great.
So I think there were a lot of preconceptions that it's challenging, but those preconceptions all went away.
Right, and to some extent, the success will also be seen. Then if it's really successful, as you said, if the science is really compelling, then it's a precursor to perhaps future missions, which is great.
Yeah, I think so. I know that since we've gone up, there's been a big uptick in other science groups who've put together proposals to go to the space station to do astrophysics, and I think it's part because NICER actually made it up there, and we're actually showing it is possible.
Yeah.
All right, so the pressure's on then, right? I mean, you got to show that this is going to work.
Yeah, we're still not quite there yet. So.
I actually want to go back to that point about what it's like to get something selected to go on the International Space Station. So I want to come back to this topic in just a minute. But so right now you're looking at getting your stuff, your main science modules from Goddard down to Kennedy in June, right? And then what you said, and that's the next step for launch on a Falcon 9 in January, correct?
That's correct.
I may actually be there for that launch, so that'll be awesome. I would love to see that. So, well, good luck, and I want to come back to a lot of these other topics as well. But I also need to get I want to get John into this as well. John Yorks, he's a scientist at Goddard, also working on the, make sure I get the acronym right, Cloud-Aerosol Transport System, or CATS, and that's always nice because the internet loves cats. So we will tell us a little bit about your project and what you're doing on the International Space Station.
Sure. One of the things the internet especially loves is cats with lasers, and that's what CATS is. It's a remote sensing laser instrument called a LiDAR that measures the vertical structure of clouds and aerosol in the Earth's atmosphere. And CATS was really designed to be a technology demonstration of some new technologies for Earth science, and also for Earth science instruments on the space station. And so it launched in January of 2015 and has now been operating for over a year.
Great. So you're already up there. You're doing stuff.
Yeah.
So you're telling me we now have videos of cats in space with lasers?
Absolutely.
That's going to be our next Future in Space hangout.
Yes, cats in space with lasers. Right, and we'll put one right next to that rubber ducky from the ducks on the gravitational waves there that Harley has behind him there. Yes, we'll get quite the menagerie set up. Okay, so you've been up there. You're up there now. And what science are you hoping to achieve? And if you want me to play any of these videos, just tell me which one, and I'll cue it up. But we want to get a sense of what you're trying to do and how well things are going since you've been up there.
Sure.
Presumably, for example, the launch went well because you're there.
That's right. So before we get into the science, I think it would be good to explain kind of how LiDAR works. I know some of the viewers aren't as familiar. So if you could play the how it works video.
Okay, I'll be queuing that up. Let me go find it.
All right. But so LiDAR systems, essentially, they emit laser pulses. And so this video kind of shows how a LiDAR does that and makes its measurements. And so let's see, it's that one. Go up a little bit.
Go up? Did I pass it? B-roll?
I think it's the third one. Up a little bit more.
Cats in the clean room, data swath.
That one.
How it works. There we go. Okay, here we go.
There you go.
All right.
And so the laser actually has crystals which create different wavelengths or colors of light, and then the laser transmits these photons, or pulses of photons, into the atmosphere, and from there these photons are reflected off of the clouds and aerosols in the Earth's atmosphere, and some of them actually enter into the instrument's telescope, and that return signal is what then is measured, and the timing between the emission of the pulse and the return of the signal is how we can determine the actual altitude of clouds and aerosols in the Earth's atmosphere.
Can you guys see this okay, this animation?
Yeah.
Okay, good. So all those dots, those different multicolored balls are the photons coming in, and then you're just shooting them down into the atmosphere, and as they hit the different parts, they scatter in a very presumably characteristic way.
Correct.
Okay. Cool.
Yeah, and so what you get, if you could bring up the image, I think it's called Cat Still. What you end up getting for the data images is kind of a vertical cross section of the Earth's atmosphere as the
one I had before. Was it this one?
No, I have one. Hang on a second. I can share it.
Okay.
Let me share it for a second. I think it's this one that you mentioned, right?
Oh, that one. Okay.
Yeah.
Yeah.
Right? Yeah.
Yeah, so what that shows is the vertical cross section. This was the case as the space station came down across Africa, and you can see dust in the lower troposphere, 0 to 5 kilometers in northern Africa. And then we see ice clouds or cirrus clouds in the upper troposphere between 10 and 15 kilometers. And then as we get more to southern Africa, we can actually pick up some smoke from biomass burning in the southern part of the continent. So this is the kind of data that we get, and clouds and aerosols are extremely important to the climate system. They both directly reflect the sunlight back to space. They can also interact with each other and cause some more complex radiative effects. And they're also important for other reasons. Aerosols are harmful to human health.
Why don't you tell us what you mean by an aerosol first? I mean,
sure. So an aerosol is think of it like a small pollution particle. Some of them are anthropogenic in nature, as in man-made, and some of them are due to fires or dust storms, and obviously the dust storm
eruptions, things like that.
Yeah.
Okay.
And so these are very small particles. Some of them can be slightly larger, like dust, and those particles reflect the Earth's radiation. Some of them can absorb the Earth's radiation and reflect the sunlight, and so that makes them important to climate, to understanding climate change.
Is CO2 an aerosol, or is that just an atmospheric gas?
It's an atmospheric gas, yeah. So aerosols are things such as sulfates and nitrates, and then dust and smoke particles.
Okay, all right. And so this map that Alberto's got up is sort of what you're seeing as is this just a snapshot, or is it a built-up composite over time?
So that's a built-up composite over time. That's probably somewhere around 20 minutes or so of data. But so we're basically, as the ISS moves along, we're getting that kind of profile, every second, or actually every 20 times a second, we're getting these profiles. And when you accumulate enough time, you get a nice curtain like we showed there.
So looking at this from my uneducated eye about this looks like an awful lot of this stuff is right over land masses where people are. So these, to me, look like they're man-made, but I suppose there's other aerosols that could be made, right, naturally? Or is this, what'd you call it? Anthro what?
Well,
Anthro something?
Anthropogenic.
Tends to be the man-made particles, and so Smoke in this region is considered anthropogenic because it's due to man-made fires, people burning down land to create more, to create better soil for agriculture. And so the smoke is definitely anthropogenic related. The dust is more of a natural effect, wind systems kicking it up and blowing it across the continent. What I don't show here is there's more data. This is our backscatter signal, but there's other parameters that we can look at to determine the different aerosol types and cloud phases, water versus ice.
Okay, yeah, because that's not plotted here. Because what I just noticed is in the upper left is this track over Africa. That's what you took. So I didn't look closely at that before. So I see now. And so you're also, of course, it makes sense that your LiDAR would get scattered by cirrus clouds. So that makes a lot of sense. So it was a cloudy day there, and the smoke.
Yeah, and so this really provides nice context to some of the atmospheric science imagers we have up in space already. They don't provide the vertical context of where the cloud and aerosol layers are, and so combining this with those other instrument data sets really allow us to determine some of the climate impacts of these clouds and aerosols.
So is that who your primary customers are, climate scientists, or are other people just generally interested in the atmosphere doing it as well?
Yeah, many atmospheric and Earth scientists, not necessarily just climate scientists. One of our primary goals actually is, because the data from payloads on the ISS are transmitted in near real time, within minutes or even seconds of collection, we're able to process our data quickly and get that data out to modeling communities, which can then improve their forecasts of some of these aerosols, which are harmful to human health. So if you see a pollution outbreak in China, or somewhere on the west coast of the United States, for instance, the hope is our data will provide better forecasts from the models of these pollution events.
So you've been up, you said it'll be a year now, right?
Yeah, it's been a year and over a year and a month.
Okay, so how long and how are you do you have any consumables? Do you run out of anything? Are you going to be running for a while now, or is there a definite
lifetime?
Yeah, so the original plan was 6 months to 3 years, and obviously we made our 6-month goal. And so now the 3 years really depends on how busy things get up on the space station. There's 25 locations for remote sensing payloads on the ISS, and they're starting to get fairly filled up. NICER is going to be coming on board. There's a couple more Earth science instruments coming on board in the next year or two. And so really it's dependent on if there's another instrument that's ready to go up that may kind of kick us off. And what might be actually nice is if we can show the CATS install video. That'll give people...
And then I want to get to some of our questions, because we're starting to get to a lot of them, and I want to make sure we get to as many as possible.
This is kind of a neat video. It shows the robotic arm installing the instrument on the space station.
Okay, let me just get to that. Okay, so there's how it works. What am I looking for?
It's scroll down one more, and that one right there.
One, okay.
Yep. And so you can see there our team celebrating. But so this is the image, or this is the video. And this is actually the Canadian robotic arm, which removed us from the SpaceX Falcon and passes us off to the Japanese arm, which then installs us into our...
Canadians are going to get jealous. Sorry.
And so you can kind of see the other different instruments on board, the different locations that are empty at the moment. and just a pretty neat video.
It is. You got these little slots. It's almost like a little container.
Yeah, and the video makes it appear like it happens a lot quicker. That actually, the whole thing took about 12 hours from removing us from the trunk of the Falcon to actually installing us.
So back in this part here. So yeah, I mean, look at that. There's these little docking ports, and there's already some in there. It looks like a shipping container almost, doesn't it?
Yeah, that's about the size of a refrigerator.
Is it?
Yeah.
Okay, yeah. Well, so that's where you're sitting. Awesome. That is a cool bit. Okay. All right. Well, good. So let me get back to the.
Want to go to questions?
Okay. Yeah. So yeah, we'll go to some of our questions now. I've got a lot of them here on the chat window, but before I do that, we've got one here on Twitter from K, which is basically gotcha, and this is a question for you, Alberto. Can I get one of those cool pins, even though I'm not in Texas?
I know. I replied to them, and I told them it's hard but not impossible. So we'll see. We'll see what we have.
You know what? I have an idea for this. Email futureinspace@deepastronomy.com with your mailing address, and I'll send it to Alberto, and maybe he can get you one in the mail. What do you think of that, Alberto? Is that doable?
He'll spend his weekends stuffing envelopes for.
Yeah, exactly. Exactly. I don't want to do that. How about we give him a list of where we're going to be?
Hold up the JWST pin. Let me see it. We got it. Let's do a little plugging for JWST. Ta-da! Look at that.
Also, we have, and so
and you have information in the back. It just is like a bookmark. Come on.
Look at that, a factoid card. See there?
A factoid card, yeah. That's
right. So that's what you get for watching Future in Space Hangouts, folks. Send me your mailing address at future.
What about cats and nicer pins?
That's what I'm gonna say.
You guys have swag? Do you guys have swag?
We have cat stickers, but not pins.
Okay. Well, we'll see what we can do. Just I'll forward the email address or the.
What about Nicer?
Yeah, Nicer's got pins.
We got a pin. There you go. See, everybody's got something. But I think it's better, instead of you stuffing envelopes or anybody in this hangout, it's better if we tell them where we're going to be and they can come and learn a little more.
You need to get to Austin, right? Dude. Get to Austin. Okay.
Well, not today, but we're going to be at other places, around the country as others will be. So.
Okay, so let's see. Adam Synergy is commenting on. Hey, let me. I wonder if I can do this. Let me see if I can screen share. This might be cool. Oh, I can. Check this out. I can screen share the comments. All right. So here's what we'll do. See, you guys are getting broadcast here. Adam Synergy is commenting. The ISS has been continually occupied since 2000.
Sure.
Bruce Caldwell wants to know where in the UK do I live, and I'm not going to tell you. Let's see. There was so Nicer. This is from Adam Synergy again. So Nicer will be placed away from the AMS-02 and its giant magnet.
Yeah, we're not too far away from AMS. The magnets are not a problem.
Okay, good.
What about are neutron stars hot or cold? That's a good question.
Yeah.
Say again.
Are neutron from Meyer? I hear. Are neutron stars hot or cold?
They're pretty hot. They're so hot they're emitting X-rays. That's what we're looking at.
Okay. And do you ever get any binary pulsar systems?
Yeah. So actually, some of our very interesting science is going to come from binary pulsar systems. Yes.
Will Nicer be? And this is from Adam Synergy. Will Nicer be hunting for pulsars in the galactic center?
We'll be hunting for pulsars everywhere. The galactic center is a little more challenging because it's a little further away and we have more absorption, but we'll be looking all over the place.
Okay, and here's a more involved one from Carl Kirkconnell. Being that close to the solar panel, is thermal radiative load from the panels a concern? Do you have a thermal radiation shield to protect you from the panels? And that would be good for you too, John, as well, to maybe comment on how are you protected?
So we, at least I think all payloads, when they go up there, you're handed a pile of requirements from the space station, about 1,000 of them. And when you're an external payload, it whittles down to about 600 or so. And a few of those have to do with thermal, how well you play thermally with everybody else. And so, we have to be compatible with this, and we've worked out what the impact is, the load from the panels. It's not a big problem.
Oh, and George Caldwell's Oh, go ahead. Go ahead, John. Comment on that as well.
I was just going to say, Keith, you know, like you said, every instrument has to go through all of these, you know, thermal and safety regulations, so it's not an issue.
I like that Keith called the requirements a pile of. So.
Okay, George Colville's asking a good question. And this sort of ties into a previous hangout. Can pulsars produce detectable gravitational waves?
So you know, that's actually one of the things. Yes, I believe that's possible. I'm not a gravitational wave person, but they are certainly a lot of mass, and a collision would be would probably give you a detectable signal if you had the right type of gravity wave detector.
And he's also asking, and because these are stellar remnants, neutron stars, usually after massive stars, like you said before, die, but not so massive that a black hole forms. He's asking, how do they die? Do they gradually fade like white dwarfs? They're not really fusing anything, are they?
No. You're basically looking at the remnant heat from the original star and the original explosion. So yeah, they're going to eventually fade away unless something else feeds it, like maybe another star in a binary system.
Okay, and are there any? So what determines the rotation speeds of neutron stars?
Well, it's basically angular momentum. So there are different terms that can add that could cause an object to speed up or otherwise slow down. But it's basically angular momentum, just physics.
Okay, and let me get to and atom synergy sounds freaking awesome. Yeah.
I have a question for John. Is that, and Keith probably remembers this. I've worked with Keith in the past, not so much John. That one of the justifications for these missions of opportunity on the space station is that because they're relatively inexpensive, they could be also technology demos, technology precursors for larger, more broadly capable future missions. So, John, is there a CATS 2 or something like that? I think you know to what I'm referring. Is there something downstream?
We hope so. You know, there's been talk amongst us, and we actually have submitted a proposal, and so we're hoping to hear back sometime soon as to whether or not we'll be able to build a second one.
Yeah. So in addition, the point I was making, and again, I think Keith mentioned this in passing, but I want to emphasize this, that in addition to being for the right kind of instrument, the right kind of science program, an outstanding platform, it is also, again, relatively inexpensive as a tech demo site for a technology demonstration.
You know what I want to do on this station, right? I want to put a telescope there and robotically assemble it.
We know this, Alberto.
Well, I think we should just 3D print a telescope.
That's also possible. There you go.
Print the thing.
Why not? No. Anyway.
All right. Well, so on this larger issue of ISS how things are selected to go there, one of the things Harley alluded to was that I guess it's implied or required that they be kind of inexpensive, relatively speaking. I mean, using Falcon 9 rockets to get nicer up, as I suppose a step in that direction too. What else does NASA look for in a mission? I mean, I would imagine it would have to be you could only do in space, like looking for X-rays. You can't do that from the ground, and certainly looking for dropping or shining things down in the atmosphere from space is something you need to be able to do. What is NASA looking for these kinds of missions? And I'll put that to either Keith or John. It doesn't matter.
I think two things, especially from CAT's perspective. One is science that really fits well from the space station orbit. And so for us, clouds and aerosols are great from the space station orbit because it provides a lot of coverage of the mid-latitudes and tropical regions where you have a lot of aerosol transport and cloud systems and a majority of the Earth's population. I think the second big thing is having some kind of heritage, whether it's in a space instrument that you know, was in operation previously, and you're kind of building on that, or a high altitude aircraft instrument that you want to kind of take to the next step and put in space. So those were kind of the two big selling points for CATS.
Okay. And what about you, Keith? You got anything to add to that?
Yeah, so NICER was competitively selected against things that weren't going to the space station, free flyers, balloon-borne experiments, and so it's a two-step process for us. First, we had to score extremely high in science that is in the national science roadmaps, for the country, and so once you rank as what they say is Category 1 science, very high-producing science that is asking fundamental questions that have been identified in decadal surveys, is important to understand. Once you've been selected for that, then you also have to fit within a credible cost bucket, and you have to have a very high probability of achieving your science with very low risk. And in the case of the space station, all of our infrastructure is up there, established infrastructure with very well-defined interfaces. So when I get my money to build an instrument, I'm not thinking about what the interfaces are. They're already very well-defined from the space station documentation, and we can basically spend our time developing an instrument that has leverages that the big investment that's already been made in the space station.
Great. Okay. Well, so that's I want to go to. So we're running out of time here, but I want to end it with this question here from Charlotte Gribben asking, "What's the future for ISS? Will new bits keep being added, or is there a new generation of ISS-2 in the planning?" And this is kind of a general question for the whole panel, including you and Harley and Alberto. Do we know what the future is for ISS-2 or ISS, and are we building any more?
Yeah, let me take a crack at this. One of the primary goals for the space station now, which is planned to extend at least through 2024, is, in addition to being a platform for the kinds of experiments and many others that John and Keith described, it is to prepare for longer duration human operations in space. One day, which is NASA's priority goal, sending humans to Mars. So the next step, it's widely believed, and NASA started putting some money into this. The next step is a habitation system, long-duration habitation system, in the vicinity, in orbit, in the vicinity of the Moon. Lots of early studies don't know exactly what it's going to be designed to do, or what it'll be designed as, but it's a long-duration habitation system, building on the space station in the mid-2020s, in the general vicinity of the Moon.
Awesome. Well, that'll be great. So there you go. So on that note, we got a bright future for the ISS. It's still up there, going strong, and new science modules are being added everywhere. With the next one coming, well, I don't know if it's the next one, but with a new one coming, and a very nice one because that's in the name, going up in January to study neutron stars. So Alberto and Harley. Oh, I'm getting an echo now. Alberto, I want to thank you for joining us in South by Southwest. I hope you guys get a lot of good feedback from JWST. I know it's really busy.
Yeah, thank you so much.
All right, and thank you.
Yeah,
Harley.
it's super busy. Thank you so much.
Okay.
Take care. Thank you, John. Thank you, Keith.
Yes, John York and Keith Jindot from both from Goddard, working on two very different science projects. I want to thank you both for joining us and telling us what you guys are doing on the International Space Station. So thank you for joining us.
Thank you.
Thank you guys for having me.
All right. Well, that's it. And Harley, do we know we'll be back next month? Same.
The third Friday of next month, and we now begin a series of Future in Space hangouts on strategic, large, highly capable mission concept studies for highly capable missions that NASA headquarters is looking for space astronomy over the next couple of decades.
Oh, that sounds great. Well, that'll be next month. So look forward to announcements from the Deep Astronomy social media channels. Subscribe on YouTube. follow me on @DeepAstronomy, and also on Facebook, like the Deep Astronomy page, and you'll learn all about these things as they come up. So on behalf of our guests and Alberto Conti and Harley Thronson, I want to thank you all for watching. This has been an amazing, a lot of fun. I want to thank you for your feedback and your comments. If you send emails to futureinspace@deepastronomy.com, I will see them, and I will. If you have suggestions for things you'd like to see on the Hangouts, please let me know, and I will talk to Harley and Alberto about them. All right, guys.
That's good.
All right. So thank you all. Thank you all for watching, and as always, looking